Hey, all right. I am here. You are here. We're all here. Let's talk about chapter 20, sound. We've already been talking a lot about waves. Hopefully you watched the chapter 19 videos. So now we're going to talk about chapter 20, and we're just going to limit our wave discussion to sound and how sound behaves. So in this lecture, hopefully we'll get through all these things. We'll talk about the nature of sound, what produces sound, the origin of sound, how it moves through the air, different things that transmit sound, the speed of sound in air. It depends on certain conditions. The reflection and refraction of sound, how sound waves carry energy. We'll talk about force vibrations and natural frequency. We'll talk about resonance, interference, and beats. It sounds like a lot, but I don't think it's going to be too bad. So let's get started. If a tree falls in the forest and no one hears it, does it make a sound? You've all heard this riddle, right? The answer is yes, of course it does. We are scientists, not philosophers. So yes, it makes a sound. Whether or not anyone is there to hear it, energy is released. So sound is a form of energy that exists whether or not it is heard. Most sounds are waves. They are made by the vibrations of matter. So for example, if you play a piano, a violin, a guitar, any instrument with strings, that sound is made by vibrating the strings, making them move. If you play the piano, you press a key, a hammer hits the string, it makes it vibrate. That's where the sound comes from. In a saxophone, you use air to vibrate a thin strip of wood called the reed, and it makes things move in the saxophone. In a flute, you move the air at the front of the instrument, at the mouthpiece. In your voice, we are vibrating our vocal cords to make all these noise. I'm doing it right now, and you are hearing a recording of me. It's awesome, man. All right. The original vibration makes the vibration of something that is larger or more massive. So you vibrate the string on your guitar or the string on, say, a violin or a cello. It vibrates the sounding board of the instrument, which is what makes that nice, loud, resonant sound that you want with a musical instrument. The vibrating material sends a disturbance out throughout the surrounding medium. It's usually air, and that disturbance exists in the form of these longitudinal sound waves. And we talked about what it means when a wave is, circles again. Look at this. Let's get rid of those, yeah? How do we do that? Like this, yeah? No, not the whole thing, just that. Let's get rid of that. Get rid of that. What's happening? We're going to get rid of this circle. I'm going to vendetta against it now. There we go. All right. So the surrounding medium is usually air, like we said, and it's in the form of these longitudinal sound waves. I wanted to underline this word longitudinal when all the craziness started happening. So we know that means the air is moving in a direction parallel to the direction of the wave travel. All right. Under ordinary conditions, the frequency of the vibrating source and the sound waves are the same. The impression, the judgment that you make about something, the frequency of the sound, is called the pitch. So if something is high pitch to you, it has a higher frequency than something that is low pitched. A deeper, bassier sound. If you have good ears, you are going to hear things between 20 and 20,000 hertz, quite a range. As you age, you tend to lose off that upper limit. Yeah. Sound waves with frequencies below those 20 hertz we call infrasonic. And you remember in chapter 19, we talked about the spectrum a little, and I told you about this word infra, and it means below. So if sound waves are infrasonic, they're below the frequency where you can hear, so they're below that 20 hertz. Sound waves that are above 20 hertz are called ultrasonic. You cannot hear infrasonic or ultrasonic noises. Who can hear what we call ultrasonic? Dogs. If you guys have dogs or a dog and you have a dog whistle ever that you used, I think maybe don't. I think they're kind of mean. Dogs don't like them, but they can hear them. You blow on this metal tube and you don't hear anything and your dog comes running. That is because to your dog, that is making a noise it can hear. And it's like, whoa, what is that noise? And it probably wants it to stop. We talked about low and high. All right, sound in air. As you know, sound waves are vibrations made of compressions and rarefactions, and we talked about that in chapter 19. They're longitudinal. They require a medium. Light waves do not. So that medium can be a solid, liquid, or a gas. Usually it's a gas. We sit around in rooms filled with air, which is a gas, and we talk. So a compression is where the molecules are bunched up close to each other, and a rarefaction, they're further apart. So when I open the window and I bunch those I'm talking about this picture here. When I open the window and I bunch those air molecules up next to each other, they can blow out the curtain on the other side. When I close the window and I'm pulling those air molecules away, now I'm talking about this one, they will pull the curtain the other way. And you know that compressions are where the air molecules are close together, and rarefactions are where they are further apart, less dense. The wavelength of a sound wave is the distance between compressions or rarefactions that are right next to each other. So here is a compression, here's the one right next to it. So if you measured that, that would be the wavelength of your sound wave. And you remember that funny Greek letter is called lambda, and it means wavelength. How do we hear sound from a radio loudspeaker? Well, it's plugged in, it has power, or it's powered somehow, a battery or something. And the unit that it's hooked up to tells it how to vibrate, basically. So it has a paper cone in it, usually, that will vibrate. And then the air molecules that are next to that paper cone, right next to that loudspeaker, are then set into motion. So the ones that are right next to the loudspeaker, they start vibrating, and then they vibrate the air molecules that are right next to them, and then they vibrate the air molecules that are next to them until it gets to somewhere you can hear, hopefully. So what is happening is that speaker is setting up these compressions and rarefactions, sound wave in the air, and you are hearing it. Any elastic substance, something that can move a little bit, will transmit sound. So a solid, liquid, gas, or plasma. We don't talk a lot about plasma. In liquids and solids, the atoms are closer together. They're going to respond quickly to the thing next to them moving, the atom next to them moving. So they transmit that sound energy with not a lot of loss. Sound travels about 4 times faster in water than it does in air, and about 15 times faster in steel than in air. So it's moving the fastest in the solid. The speed of sound, we talked about this a little bit when we were in chapter 19. I said it would depend. It depends on the wind conditions where you are. It also depends on the temperature and the humidity. So in dry air at 0 degrees Celsius, it's moving at about 330 meters per second. So 0 degrees Celsius is 32 degrees Fahrenheit. In water vapor, it's going to go a little faster, and it travels more quickly in warm air than it does in cold air. So each degree that you go up over that 0 degrees Celsius mark, the speed of sound is going to increase by about 0.6 meters per second, a little over half a meter per second. In water, it's 4 times roughly what it is in air, and like we said in the last slide, in steel, it's about 15 times what it is in air. So let's have a question. You are watching a person chopping wood. You note that after the last chop, you hear it 1 second later. How far away is the chopper? And I'm going to remind you that the velocity of sound is 330 meters per second. So if I hear the sound 1 second after it happens, is that person 330 meters away, more than 330 meters away, less than 330 meters away, or there's no way to tell? I know what you're thinking. You're thinking, well, there's no way to tell. She said it could depend. I don't know the temperature. We're going to say 330. Roughly, they're 330 meters away. You hear thunder 2 seconds after you see a lightning flash. And you guys do know that that's the same event. The lightning happens and it makes both that flash you see and the noise that we hear as thunder. It's the same thing. So I see it, and then 2 seconds later I hear it. So how far away then would that lightning be that made that thing happen? 340 meters, 660 meters, more than 660 meters, or there's no way to tell. And it should just have meters, not this meters per second business. So what do you think? What? Oh, yes, you are correct. 660 meters, not per second. It's just 660 meters away. So let's talk a little bit about the reflection of sound. That is what happens when sound, you make a sound wave, it encounters a surface, and then it comes back to you. We call that, you've heard this word before, an echo. Multiple reflections are not called echoes, they're called reverberations. But you know, if you go into a cave or you're standing by a canyon or something and you call out, hello, you will hear that a couple times. You hear it come back to you. That sound wave reaches that hard rock of the cave or the canyon, and then it hits it, and that sends it back to you, and you hear it again. Reverberations are best heard when you sing in a room with, what kind of monster carpets their walls? In a room with carpeted walls, hard surfaced walls, open windows, or none of the above. And to answer this question, you all know the answer. Think about, where do you like to sing? You like to sing in the shower, right? You like to sing in the bathroom because you have hard surface walls there. They have tile, they're hard surface, so you get to hear all that reverberation and you sound great. So hard surfaced walls. If you're singing in a room with carpeted walls, I don't know what to do for you. If you're singing in a room with carpeted walls, what's happening then is all that material, all those things are going to absorb that sound wave instead of sending it back to you. All right. Fabric is absorbent in terms of sound waves. So let's try to solve a problem. Let's consider a person attending a concert. It's being broadcast over the radio. So radio waves, I want to tell you, move at the so-called speed of light, and I've written that down here for us. So the person attending the concert is sitting 45 meters from the stage, and they're listening to the radio broadcast over one ear. So I'm sitting in front of the stage with one ear, I'm listening to what's going on in front of me. With the other ear, I'm listening to the radio broadcast, is what it's saying. So suppose that radio signal is going all the way around the world before it gets to you, before you get to hear it. I want to know which ear is going to hear it first, the ear that's listening to what's happening live right in front of me, or the ear that is listening to that light speed signal. Okay, so I know that time is equal to the distance traveled divided by the velocity we were traveling at. So the time it's going to take you to here from the stage, it's the 45 meters you are away from it, divided by the 340 meters per second we're going to say sound is traveling at here. And if you do the math, that's going to take about 0.13 seconds. The time it's going to take for you to hear the radio broadcast, remember, it's not going 45 meters, it is going all the way around the world. So that's about 40 million meters, or 40,000 kilometers, 40 million meters. And we're going to divide that by how fast an electromagnetic wave travels. That's what we call the speed of light. And when you do that, you will see you get about 0.13 seconds. So in the time it takes sound to travel 45 meters, light or a radio signal has been all the way around the world. And the next question is what will be heard first, and you know, because you just did the math, you're going to hear both of them at the same time. And then it takes you through a little explanation of the math again here, but we already did that. The name that we give to the special branch of the study of sound is acoustics. And you guys have heard that word before. And you'll even, if you're a musician or if you're going somewhere to see musicians play, you might talk about the acoustics of wherever you're setting up. Do things sound good here? Do things not sound good here? So a concert hall, they're going to set things up in a special way, and they're going to build it a special way to maximize what we know about how sound behaves so that things sound as good as they possibly can. Refraction is what happens when these waves get bent. So sound moves more slowly in cooler air. Let's get this out of the way. We'll put it back in a minute. Sound moves more slowly in cooler air than it does in warm air. So that causes these sound waves to get bent. It can also be affected by the temperature of wherever you are and how the wind is behaving. So when air near the ground on a warm day is warmed more than the air above, sound tends to bend upward, downward, or at right angles from the ground. So let's think. We're moving, it's the same sound wave, it's moving faster here at the bottom because that's where the warmer air is, and it's moving more slowly here at the top. So the distance, the bottom is going to be more than the distance at the top. So that's going to cause a bending in the upward direction. In the evening, when air directly above a pond is cooler than the air above, sound across the pond tends to bend in which way? Upward, downward, at right angles to the ground makes no sense. Just let's say upward or downward. So here's our pond. We know it's cooler here. It's warmer here. So sound is moving more because it goes more quickly in the warmer air. So it's covering less distance in the same time where it's cooler. So that's going to cause it to bend down. Multiple reflection and refractions of ultrasonic waves are what we use when we use an ultrasound to image. And this is a picture, it looks like of a fetus, I guess. We use ultrasound for all kinds of imaging these days, though. Anytime they're wanting to see soft tissues that are inside, we might use ultrasound to look at them. So what happens is that ultrasound, they put it right on your skin, right on you, and it sends high frequency sounds into the body, and then the way they come back, it makes this picture so that we can see what's in there, what is happening. So that is used in the place of X-ray. There are a variety of reasons you might not want an X-ray, not just the radiation. And a lot of times this ultrasound can give us a better picture of what's happening anyway. Dolphins, you may or may not know this, use ultrasonic waves that they send out to enable them to like see where things in their environment are. They see with this. So they make a picture with these ultrasonic waves the same way we make a picture with ultrasonic waves when we do an ultrasound inside your body to see what's going on there. So ultrasonic, you know that they are a higher frequency than what we can hear. Force vibration is what happens when we set up vibrations in something by a vibrating force. So our example is if I have heavy machinery standing there running, it's vibrating, right? So the factory floor that the machinery is sitting on is going to vibrate. It's going to vibrate with the same frequency of the machinery. And that is probably fairly intuitive to you. It's pretty easy to picture that and accept that. This might not be so easy to accept. Every object has its own natural frequency. It depends on its elasticity, like how easily does it give, and the shape of the thing. So I want you to picture like a big, big glass like this, right? And you're like, oh no, Miss M's doing art. It's not that bad. So this is a big glass, and then we have like a smaller glass, and it's thin and tiny. Well, this one is bad. We'll give it a solid stem. All right. If you walked up to these and with like just a little gentle tap with like a knife or your finger or something, you know that this glass or crystal, whatever it's made out of, is going to like ting, right? So which one do you think is going to have the lower sound? This one. This one will have the lower frequency sound. So it has a natural frequency that's dependent on its shape, like all things do. With glasses, we can hear it. So this is going to be higher. I was working on breaking that glass for you guys. If I can do it, I will post the video so that you can see it, but it's really quite difficult. I'm still trying though. So like I said, that natural frequency is dependent on the thing's shape. So with glasses, you can easily hear what the natural frequency is. So the bigger and more like bowly shaped it is, the lower the frequency is going to be, and the smaller and thinner the glass is, the higher its natural frequency will be. So resonance is what we give the name to the phenomenon, where we see vibrations happening when we match that object's natural frequency. So that's the thing that breaks the glass. That's how opera singers or professional singers can break a glass. They would match its natural frequency. So I'm going to encourage you not to try this at home, and do watch it on YouTube. And if I can't do it myself, I will at least post a YouTube video with other videos that I post for you so that you can see it. But if I hold the glass next to me, next to my head, and I produce a pitch at its natural frequency, that causes it to vibrate. If I can make that, or if anyone can make that pitched loudly enough, it will cause that to vibrate strongly enough that it breaks. Other examples of natural frequency, if you've ever been on a swing, you know that at some point you kind of fall into a groove with this swing. It's you're then moving at that swing's natural frequency. Troops marching in rhythm with the natural frequency of a bridge would cause that bridge to vibrate, and it's going to vibrate strongly, and what's going to happen is that bridge is going to fall down. So when large numbers of people walk across a bridge, they're actually instructed not to walk in step, because you don't want to fall in with that natural frequency and cause that structure to vibrate, because we do not want any bridges to break. I already told you about that. So this is a really dramatic example of a bridge, and it began to vibrate at its natural frequency. And this is the Tacoma Narrows Bridge, Tacoma Narrows Bridge. And I will also put up, it was captured on video. I will put up the video of this. You get to see this bridge just swinging and swinging away in the wind. So what happened was they didn't build it very well. And since this disaster, engineers do things a little differently. This caused a shift in how bridges are engineered. We do a lot more testing with models now before we just go ahead and say, yeah, that design looks good, let's slap that bridge together and put it up. We will build small models of it and see how it behaves under certain conditions, whereas they didn't really do that so much before. But what happened was the wind started to make this bridge move. It then began to move in its natural frequency. That set up another weather pattern around it that was kind of like self-reinforcing, and it began to vibrate more and more strongly, and the bridge eventually collapsed. Interference we already talked about, but it certainly happens with sound waves. It's property of all waves and wave motion, so of course sound waves. When we put those waves, superposition means taking a wave, putting it right on top of another wave that's there in the same place. So they either reinforce, that's this one, or they cancel. So this is our constructive interference, constructive. And this is our destructive interference when they cancel. So interference is a property of what? Sound, light, A and B, or neither A or B. I told you, of course, anything that's a wave, you know light's a wave, you know sound's a wave, so it's going to be both of them. And here's the picture that we saw in chapter 19. Again, this is that interference pattern. So you get increased amplitude when a crest aligns with a crest, and you get decreased amplitude when the crest aligns with a trough. And here you can look at this. If I have this and it's exactly in step with this, I get my resulting wave. What I see is going to be something that has higher peaks, higher crests, and deeper troughs. The same with a sound wave. They are in phase. When the crest is overlapping with the crest, we say that it is in phase. So the same thing can happen with a sound wave. When I get a compression overlapping with the compression, I get a stronger compression. If they're out of phase, the opposite thing happens. You see here we have a crest. In the same place, we have a trough. So I'm going to get nothing. I'm going to get destructive interference. Same with a sound wave. If I have a compression overlapping with a rarefaction, I'm going to get canceled out sound. They are out of phase. So destructive sound interference we can actually use to our advantage. So picture someone whose job it is to run a jackhammer all day long. The jackhammer can now be equipped with a microphone that produces a mirror image sound wave. So say this is the jackhammer. If I can write, this is the jackhammer. This is that mirror image sound wave, mirror image. So the jackhammer is equipped with a microphone that produces a mirror image wave, and that is fed back to earphones that the operator is wearing, and it cancels out. So that person does not then suffer hearing damage from listening to this loud jackhammer all day long, because that pressure wave isn't hitting their eardrum. It's getting canceled out there at that space where their ear is. Sound interference in stereo speakers. You might know about this already intuitively, or you've investigated it. You know, when you are setting up your home theater system, or you're setting up music in your room or something like that, you might move your speakers around. If you have speakers that you can move around, you might think, well, this doesn't really sound good there. I'm going to put it over here, and I'll put this one here, and eventually you get to an arrangement where that sounds really good. If you have them not placed as advantageously, what can happen is the sound wave from one speaker will interfere with the other one, and it'll cancel out some of the noise. And this is noise that you want, so I don't want to do that. What are beats? Beats are periodic variations in the loudness of a sound, and it's due to interference. So they occur actually with any kind of wave, but we're going to talk about it with sound waves right now. So these two tuning forks are at different frequencies, and if they're sounded at the same time, those sound waves are going to interfere with each other. So wherever we have a crest line up with a crest, we're going to get constructive interference, and you're going to hear that. You're going to hear that it's louder here. And whenever we have a crest with compression with a rarefaction, we're going to get destructive interference, and it's going to be softer there. And I've covered up that word destructive, and I don't really want to do that. So this, and I'm going to put the question to you before I answer it, which one has a higher frequency, the bottom wave, this one, or the top wave, the other one? I can see compressions that are closer together in the bottom wave, so that one has the higher frequency. It's not very neat. I apologize. So the applications of this phenomenon, these beats that you can hear when things are at different frequencies, heard when things are at different frequencies. Beats are heard when two sounds are at different frequencies. So we can turn this to our use. If you're trying to tune a piano, that piano tuner is going to listen to when they hear the beats disappear. So they're going to have a set of keys, like a set of tuning forks. And so say, I know I need this string to exactly make this noise. So I sound the tuning fork, I sound the string, and I wait till those beats disappear. That means that those frequencies match. You will not hear beats when things are at the exact same frequency. If you've ever played an instrument with other people that play instruments, you have to tune before you can play. So you will sound your instrument on a certain note, and you will make whatever adjustments you need to make those beats that you hear at first go away. So you will not hear beats when things are at the same frequency. When two frequencies match exactly, no beats. All right. And that's really all I wanted to say about chapter 20. I hope you learned something.